morning, students. I welcome you all for another lecture on the course Computer Architecture and Organization. In today's class, I am going to discuss about the concept interrupts. So first, what is meant by an interrupt? Generally, an interrupt is nothing but a disturbance signal from CPU point of view. At the same time, it is a request signal from the device which issues the interrupt signal. So I repeat, interrupt is a disturbance signal from processor point of view. At the same time, it is a request signal from the device which issues this interrupt signal. So why we are going to learn this interrupts, especially in this I/O organization or input-output organization. In the last class, I discussed about different I/O techniques or I/O data transfer techniques. In that, the first one is programmed I/O that we discussed, and the second one is interrupt-driven I/O, and the third one is direct memory access. So today's class, we are focusing on interrupt-driven I/O. So in that, the important role was played by these interrupts. So in this class, I am going to focusing on explain about the interrupts. Fine. So what we are going to learn in today's class? If you are thinking that direction, if any device wants a service from the processor, then what the device can do is it simply issues an interrupt. Once our CPU receives that interrupt, what it do? Or how an I/O device send a request signals to the CPU. Once a CPU receives that request signal, what it will do? If the CPU receives multiple requests from multiple devices at a time, what it will do? These things we are going to discuss in couple of classes, this class and upcoming classes. So I would like to try to finish as much as possible in today's class about these interrupts. Yes. So in programmed controlled I/O or programmed I/O, the processor continuously monitors the status of I/O device. If the device is ready or not, it continuously monitors that. Why? Because if the device is ready, the CPU can communicate with the device for the purpose of either the CPU receives something from the device or it may transfer something to that device. In this particular case, the CPU was wasting its valuable time, because we know that the main function that was done by the CPU was data processing. But in programmed controlled I/O, what a CPU can do is, instead of doing that, what it do is, it will go on to monitor the device status repeatedly until it will find the device is ready to communicate with the CPU. In order to overcome that particular difficulty, we shifted to the second type of I/O technique or I/O data transfer method was interrupt-driven I/O. So in this case, the interrupt signal plays a vital role. It means in order to reduce the idle time or waiting time of a CPU, whenever the device was ready to communicate with the CPU, the device informed that information to CPU by issuing a special signal, which is called here interrupt signal. By issuing this particular interrupt signal, our I/O device is ready to communicate with the processor. So you remember in an interrupt-driven I/O, whenever the device was ready to communicate with the processor, that instant the device issues a special signal which is called an interrupt signal. Due to that, what happens is, in previous case, our processor was continuously monitoring or repeatedly verifying the status of I/O device. The time here was saved because in this case the CPU can't waiting or can't check the status of I/O device in repeated or in regular time intervals. In this case, the CPU can do some other task which is useful for the processor. That means your CPU can engage with doing of some other data processing function. instead of repeatedly verifying the status of device. In that aspect, this particular data transferring method is better one compared to previous one, that is program diagram. In case of this, whenever the device was ready to communicate with the processor, that instant only the concerned device issues a request signal to CPU, which is called an interrupt signal. Once our CPU receives an interrupt signal, what it do? So that we can go on to verify this. So for example, you can take this. The processor can perform other useful tasks while it is waiting for the device to be ready. That's what I'm seeing. Here our CPU can do some useful work, and your CPU attend for I/O device operation only when the device was ready. This is an advantage of this interrupt driven I/O compared to programmed I/O. What happens if our CPU receives an interrupt? For example, right now our CPU executing this particular program. This program has some n number of instructions. Our CPU executes this program instruction by instruction without any difficulty. While executing instruction I, this is instruction I, that incident an I/O device issues an interrupt signal to the CPU. Then what our CPU can do at this moment, if you think in that direction, your CPU what it does is, it first finishes the executing instruction I completely. Thereafter, what it does is, what are the information that is related to this executing program, it will store that information on stack. That means which information it can preserve on the stack before providing the service for an interrupt. Here what I am saying is that the execution of instruction number I, your CPU receives an interrupt from an I/O device. That means some I/O device wants some service from the processor. That means your CPU has to go and execute a program which was related to that interrupting device. That program here what we can call is interrupt service routine ISR. Before shifting our execution from this particular instruction to here, our CPU has to preserve this particular executing program information in the stack. Which information we can store? What is the necessity to store the information of this program stored on the stack? If you are thinking in that direction, after execution of this instruction I, my program execution was shifted to this interrupt service routine. After successfully completion of this, I may come back to at this point only. Why? How my CPU can able to know I just moved to this position. Right? How it knows? So for that particular question, we have an answer. That is, before shift our execution from this executing program to the interrupt service routine, we have to go and store particular information of this program temporarily on the stack. In that case, what we do, if the execution of this instruction is going on in my system, the incident, the program counter PC points this I+1 instruction address. We know that. Because the job of program counter is, always it holds the address of next instruction. What we are going to execute it next, or which instruction we are going to fetch it from the memory. That instruction was held by this program counter PC. Right now, the instruction I was executing in my system, that incident, the program counter PC points the address of the instruction I+1. So once our processor identifies after execution of this instruction, I received some interrupt. Then what it do is, first of all what it do is, it stores this next instruction address, that is a PC value on the stack. This is the first thing what it do. And the second thing is, up to this instruction I execution, this program has certain status. That means up to this instruction execution, for example, you can assume the carry flag is set to 1, sign flag also set to 1, and overflow flag equal to 0, and 0 flag equal to 0, like this. There is certain status for this program up to this instruction. This status information is available on the status register or a flag register or a condition code register. If I come back after execution of the service routine to this stopped program, I need a same status information. That means I need same conditional codes information. If I want to get the same status information, after come back from ISR to your previous stopped program, what we have to do is you have to go and copy the flag register information or status register information or condition code register information on the stack. The second thing what we'll do is we can preserve status register information in the stack. That was the second. And coming to the third, for example, up to this particular program execution, you may use certain registers of CPU. For example, up to this, I may use a register R0, R1, R2, and so on. I use up to R7. Out of these 8 registers, I may go and use these 3 registers in this ISR execution also. If I use these 3 registers in this ISR execution, what happens is, if I come back after execution of this ISR to previous stopped program, these registers may not have the same value what previously was exist before shifting execution from this program to interrupt service routine. For example, before shifting execution from this to this, R0 value is some 20H. Let me assume these are registers are 8-bit registers. And R1 is equal to some ABH. And R2 is equal to some 67H. These are the values. If I not store these values temporarily on the stack, what happens is, these are same registers are used in the execution of this interrupt service routine. By execution of the instructions which are present in this interrupt service routine, at the end of that, I identify that R0 value is 00H, R1 value is some 23H, and R2 value is some CDH. After execution of this service routine, this is the value. Right? Then what happens? If I come back from this service routine to this, previous case R0 value, R1 value, R2 values are different compared to what are the values are exist in R0, R1 and R2 after execution of interrupt service routine. So, if I continue with these values in the execution of the rest of the instructions of this program, at the end I may get the wrong results. To avoid this difficulty, what we will do is, instead of copying of all the registers information on the stack, which are the registers we are going to use in ISR also, which already use those registered in the program execution, only those specific register values we stored on the stack. That means the third information what we can copy in the stack was different CPU registers. Different CPU registers. These values we can copy onto stack. Once again, I clearly mentioned, guys, I am not copying all the CPU register values on the stack before shifting execution from the current executing program to interrupt service routine. I can only copy the registers which are common for both the executing program and ISR. Only those are few register values I copied onto stack. After doing these 3 steps, that means after copying PC value, after copying status register value, after copying some CPU register values in the stack, then we can go and calculate the starting address of this service routine. We can calculate the starting address of this service routine. Once we calculate the starting address of this service routine, by means of any different method, we have a different methods for calculation of a service routine address. So by using any one method, once we finalize the starting address of service routine, that value was copied onto the program counter PC, then and only our execution was shifted to here to here. Then we start the execution of service routine. We successfully execute all the instructions which are present in this service routine. I clearly tell you in the last class, guys, when I am talking about the branching instructions, one of the unconditional branching instruction which is IRET or RETI, those instructions we are using as a terminating instruction for interrupt service routine. It means here the last instruction is, it may be RETI or IRET. in different processors they are using different instructions. The meaning of both instructions is same. RETI or IRET both indicate same, that is termination of interrupt service routine ISR. By execution of this particular instruction, the execution sequence again changes from interrupt service routine back to our previous stopped program. Once you are moving execution from this ISR to a previous stopped program, whatever the information we was stored previously in the stack, before shifting execution from the current executing program to interrupt service routine, the same information we take in reverse order from the stack. That means once you are moving execution from here to here, the first thing what we will do is we can go and access the CPU register values from the stack. That means whatever the operation we've done at the last, before shifting execution from the program to the interrupt service routine, that operation we do first once you shift our execution from interrupt service routine back to the main program. So this is the first task. The second task is we retrieve status information, status register information from the stack. This is the second one. And last one is we will go and get the PC value, that is the next instruction address. Once you are doing these three steps, once you are performing the last step, that is accessing the information from the stack, which information you are accessing last? That is the program counter value. Once you retrieve PC value from the stack, that is straight away goes to the PC, then and only our execution was changes to this. Once we come back to this, we can go and execute the rest of the instructions continuously. This is a scenario what a processor can do if it receives an interrupt. I hope you understand. If a CPU receives an interrupt from an IO device, what it do? The first thing, it is very clear, it will go and execute whatever the instruction that was executing right now. It completed the execution of that instruction. Thereafter, what it do is, it has to preserve the current executing program, these informations on the stack. Yes, once you come back from interrupt service routine, again we are moving to our previous stopped program. We stopped at instruction I+1. After successful execution of interrupt service routine, again we start our execution from the instruction I+1. We know this. And one more thing, we know that before shifting our execution from current executing program to interrupt service routine, we preserve PC value. There is no doubt at all. That is in the stack along with the status information as well as some of CPU registers which are common to both the interrupt service routine and current executing program. And coming to the next here, important one is what this interrupt latency. This interrupt latency is nothing but the delay amount. What is the time that can be taken by the CPU after receiving an interrupt and to provide service for that interrupt. There is a time gap between receiving the interrupt from an IO device and providing the services to the interrupt. So the delay between these two incidents, that what we can call is interrupt latency. So here I written as the interrupt latency is nothing but the delay between the time an interrupt received by your CPU from an IO device and the start of execution of interrupt service routine ASR. For example, my CPU receives an interrupt in time instant T1, but it can't start execution of service routine of received interrupt immediately or at the same time instant T1, but your CPU start execution of service routine in T2 time incident. Then the difference between this T2 minus T1 we can call that was interrupt latency. So this is one of the important parameter in interrupts you have to remember. Fine. And next important thing is how our CPU recognizes interrupts which are issued by an IO device. Because we know that each and every IO device is able to generate its own request signal. The generated request signal of an IO device was transferred to your CPU in different ways in different systems. For example, in some systems, each and every IO device has its own interrupt request signal. With the help of that signal, the corresponding IO device transfers its request signal to the CPU. In some systems, what happens is all the devices which are present in the system itself, they share common request signal. With the help of that one only, all the devices send their request signal to a CPU. There are two different things. So, at this moment, I would like to discuss about if a system has only one interrupt request signal that can be used by all IO devices. How an IO device send their request signal to CPU, that I am going to discuss with the help of the simple diagram. So see here guys, this is our processor and this is our interrupt request signal which is a low signal INTR. It is always connected to a VDD. It is always connected to VDD. So let us then assume these are the different switches. With the help of switches only, our IO devices send the request signal to a processor. So this signal is inward to your processor. If for example, the device which uses this switch, that instant the switch was closed, then here the logic level present on this INTR signal is 0 because here the ground was connected. So automatically here logic level is 0 was present. That can be received by your processor. That means in regular time intervals, what your processor can do is, it will go to verify the status on this INTR bar signal. Here INTR means interrupt request. So here the signal is INTR bar. That means INTR is an act to low signal. It is an act to low signal. Once no device use this interrupt request signal, the time all the switches are open, that incident this INTR signal is connected to VDD. That incident the logic level present on this INTR bar is equal to 1. Once your CPU identify logic level on INTR bar is equal to 1, that means no device in the system send their request signal to me. So that is the meaning of that. So you remember the simple logic here is whenever a device send a request signal to the processor, that instant the logic level on this INTR bar signal is changes to 0. If no device send a request signal, then the logic level present on this particular INTR bar signal is equal to 1 because that incident this signal is connected to VDD. So here the switches plays a vital role. Here important thing is this INTR bar is equivalent to logical ordering of all these interrupt request signal. Means here I have INTR1, INTR2 and then INTRn. That means my system has n number of devices. Each and every device is able to generate an interrupt request signal. Those interrupt signal here I can call as IR1 to IRN. But these request signals are transferred to your processor with the help of only one signal, which is INTR bar. So here this INTR is equal to INTR1 plus our logical R with INTR2 logical R with and so on plus INTRN. That means if any number of IO devices send their request signal to the processor, that instant they will use only one signal. So no doubt once your processor identify logic level 0 over it, then automatically it identify that I receive an interrupt. You remember friends, our processor regularly verifies the logic level on this INTR. It verifies the logic level of INTR bar only when? Before starting of every instruction. That means after execution of every instruction, before one start the next one, it will go and verify the logic level present on INTR. So here only one device send a request, it easily identifies only that device send a request. If you have multiple devices send a request signal, then how your CPU can recognize which device send it request. But one thing you have to remember friends, that is, whenever a device get a service from the processor, or whenever the device get a response from the processor, that means once your processor going to provide a service for any request, it issues acknowledgement signal. Once a device receives that acknowledgement signal, then and only it change logic level on INTR signal. It change that instant only the logic level on INTR signal. That was an important. So until it receives an acknowledgement signal from the processor, it will maintain the logic level on this INTR bar is equal to 0. Once it receives acknowledgement signal, then it changes logic level on INTR bar signal from 0 to 1. That means the device gets a service from the processor end. Here there is a problem. If this is type of a scenario we are used in the system, at a time multiple devices send their request signal, it is a tough task from the processor how our processor identifies which device issue the request signal. So here it will use a different mechanisms to identify the interrupting device. In that case we are using hardware polling or software polling, bus arbitration. There are different methods we are using to identify which device issues an interrupt request signal to the CPU. So in the next class I am going to discuss about how our CPU can handle the multiple interrupts. So thank you for patient listening. So meet in next class. Thank you very much. Have a nice day.